We have Mike Fremaux. Wait, yep. And we have Dave Storch. Yay, there you go, finally. Mike is currently a chief engineer for the Intelligent Flight Systems Division of the Research Directorate. And for most of his 36 years here at Langley, Mike has been associated with Flight Dynamics branch as a researcher, as assistant branch head, and even a branch head prior to being selected for the Intelligent Flight Systems Division Chief Engineer in 2020. He's also his other duties as assigned, because I remember working with Mike on multiple things. He was an executive assistant for the center director in 2005, associate director within RD in 2011, and also in 2022. He received his bachelor's and master's degrees from LSU, as well as a master's degree from George Washington University. And since 2015, Mike has been the center's lead for advocacy and development of the new FDRF. So congratulations on all of that. And this will be, as we've mentioned multiple times, the first major wind tunnel facility constructed in the agency in over 40 years. So thank you, Mike, for coming to be with us. And since these guys are going to tag team each other, I decided I'm introducing you to Dave right now. So Dave is a project manager in NASA's Langley Research Center's Projects and Engineering branch, who is responsible for the design and the construction and activation of complex aerospace research facilities. Prior to coming to NASA Langley in 2020, he was in the U.S. Coast Guard's Yorktown Training Center. He's an engineer officer in the Army Reserve. And so actually, I'm very glad we did move this, because we weren't going to see Dave next month, because he was going to do some reserves. He has extensive employment in the commercial construction sector also, as well as superintendent and project manager on design-built projects for a large-scale general contractor. He holds a bachelor's degree in mechanical engineering from the U.S. Military Academy and a master's degree in national security management from the University of Maryland University College. Go Terps, I'm a Terp too. Okay. And strategic studies from the U.S. Army War College. Dave is currently a senior project manager for the design and construction of the FDRF. So let's welcome Dave. So since I just found out last night actually, that Charlie wasn't going to be here, I didn't get a chance to, like I normally do. Okay, fun fact, you two. Mike, what's a fun fact? Usually that's what I do when I introduce our speakers, is a fun fact. Dave Young can attest to this one. Fun fact. And now come on, be good.
So Kathy sprang this on me about 20 minutes ago.
Yes.
Charlie just conveniently forgot to mention that when he called me on Sunday.
That's right.
Doing this thing. So, thanks, Charlie.
Yes.
So I couldn't think of anything really great, but I will say that given the fact that I grew up down in Bayou Country, I grew up in a town called Rayne, Louisiana, and that's spelled R-A-Y-N-E, and it was named for the engineer who brought the railroad through town about 2 miles north of the original town, which was called, I'm not kidding you, Poo-Pooville. So they decided to change the name to Rayne, which I thought was a good move. But our claim to fame is it's the frog capital of the world, the International Frog Festival. So I grew up eating frog legs kind of by force more than anything. And I will tell you, the fun fact is it does not taste like chicken, I promise. It looks a little bit like it, but it's totally different thing.
Doesn't do it. All right. Okay, Dave. He said, I told him to tell you, and he said.
Right. So if he heard 20 minutes ago, I heard about 5 minutes.
Yes, on the way over walking.
Any fun fact either, as you can probably guess maybe from my resume, I have no idea what I want to do when I grow up. And so I kind of just split around to things that seem interesting at the time.
That's great. All right. Well, let's give him a great hand. Welcome. And thank you for coming early and doing it. And you got it.
So let's see, I want to get the, so there are folks online, I assume, and I want to fire up the laser pointer here. So the way this tends to work, Dave and I have done this similar talks previously, kind of lost count at this point. You know, the Mike and Dave show, we kind of do a little tap dancing, a little soft shoe, and then we get on with it. But we're just going to go straight into the presentation this time. And let's see, we're already in presentation mode. So I usually like to walk around and point, but I'm going to stay here with the microphone and use the laser pointer here for folks. So we'll go over this because we've already been introduced, but we're going to talk about the Flight Dynamics Research Facility today, or FDRF. And one other fun fact about that, and there might be a couple of folks in the room that already know this, but FDRF isn't the most inspiring abbreviation or name for a facility, but Dan Murray, my former branch head, and I were putting in a proposal to get some funding to do a study many years ago. And we had about 30 minutes to put the charts together and send it in. And it was like, what are we going to call this thing? So we called it the Flight Dynamics Research Facility. You know, imaginative engineers, never dreaming that that's what would end up being on the place. So there you go.
As of this morning, it's literally on the place.
Oh, that's
if you
right.
haven't driven by it, the entrance canopy above the front doors there now has that name in like foot tall letters right across the canopy.
So no redos at this point.
Right.
So all right. Well, let's get on with. And by the way, please ask questions as we go. Just call out or raise your hand or whatever. It's not an AIAA talk. This is just conversations. So away we go. I hope those in the audience will forgive me for using reading glasses. I'm sure there are a few who do the same thing. So what is the Flight Dynamics Research Facility? Well, I won't read all of these bullets, but basically what we're trying to do here is, because we have right now two very aging but very important facilities, the 20-foot vertical spin tunnel and the 12-foot low-speed tunnel located over on Langley Air Force Base, that are in excess of 80 years old. They're still operating, but as you can imagine, they're more and more difficult to maintain. The performance and the capabilities are not where we'd like them to be because we're doing things that were never designed for. So the goal originally was to have a modern capability that we could take forward for the next 40 or more years. And also what we wanted to do was shrink the footprint, because this came up kind of in the time of Newtown, where we wanted to shrink the footprint. We wanted to bring everything closer into the main campus. And so the idea of consolidating the capabilities of two existing facilities into one was very appealing. So we could shrink that footprint literally in square feet. And then we could also have a facility that had a lot more capability than either of the two existing facilities. So this is a case where the sum, is greater than the parts and all that. So without going through all this, it's the first one in over 40 years. We have leveraging these capabilities. And one other thing, as you'll see as we go through, as we were trying to build the case for doing it, why does the agency need to do this? What are the things that really make it worthwhile in doing? One of them was, if you accept that we need the kind of facility that can do flight dynamics, flight mechanics type work, is that you have to have something that's going to remain inexpensive in a relative sense. It's going to be flexible and adaptable into the future, which is the very reason we still have two facilities running that are over 80 years old. And I do want to say, as I'm looking out in the audience and seeing so many familiar faces, and it's great to see everybody. There are several people in this room that this project would not be existing if it weren't for their really key contributions, and you know who you are. And I mean that. It's been as a very tortuous path, but there have been very key points where if somebody hadn't done something or said something or made a case, we would have gone on a different fork in the road. Probably not a good term to use right now. Sorry about that. A different path. Let's just leave it at that. So, all right. So moving right along. So these are, and I'll try to use my little laser pointer here. The existing facilities over on Langley Air Force Base. On the left, the sphere is the 12-foot low-speed tunnel. On the right, the inverted cone that has all the nice blue tarp over it. Where the corrosion's being repaired is the 20-foot vertical spin tunnel. There are two auxiliary buildings. On the left is the building 646, which has the drive systems and storage and things like that. Fun fact there is the predecessor to the current spin tunnel, the 15-foot vertical spin tunnel, was actually in that barn. It just was an open jet vertical tunnel that blew out the top in that barn, and that operated for several years up through World War II in parallel with the new tunnel. They were both operating pretty much continuously during the war to do all the testing that needed to be done. The 12-foot low-speed tunnel, and I'll tell you a little bit more about that in a second as well, but it was built to do a very specific type of testing. We often get the question, people drive up and say, oh, is it hypersonic? At Mach 0.02, probably not, but there's a very specific reason it's a sphere, and you'll see why in a minute. So here, you see here on the bottom, we have the kind of the characteristics, the velocities that they can run, the dynamic pressure, things like that. Very, very low speed, but very adequate for doing a lot of the work we do. However, there are a lot of good reasons we want to have higher speeds, we want to have much better flow quality, and the new tunnel over on the right, the FDRF, we have requirements that it has to meet these numbers in terms of maximum air speeds, et cetera. So that's where, and Dave's going to talk more about that when he gets to his part, which is the design construction part. But the contractors have to meet these, and it's on them to meet them under a design build approach. So he'll give you all the lowdown on that. Let's see. Little history. So in this picture on your left is the 12-foot low-speed tunnel under construction back in 1933. Is that right? No, that's a typo. Well, that's an 8. Oh yeah, it's an 8. Okay. I said 33. That can't be right. So it was built, as you see up at the top, as the 12-foot free flight tunnel, not the 12-foot low-speed tunnel. And they actually flew small models, dynamically scaled models of biplanes and things like that in this tunnel using what remote control was in those days, which was wires coming out of the model. They had bang type controllers, electromagnetic controls, and they did things like pilot inputs. What does that do to stability and controllability and things like that? So that was the reason it was built that way, because the entire test section was on pivots and hydraulically actuated and could actually pivot to the pitch angle or the flight path angle of the flying aircraft. On the right, you see the completed 12-foot tunnel, free flight tunnel. And to its left, they're building the 20-foot vertical spin tunnel right next door. So that's in 1940. I always point out where the riverbank was. This is before anybody ever talked about sea level rise, okay? So I'm assuming that was at high tide, but still, it's lapping at the concrete. I mean, they built it up a few feet, but after Isabel, I'll never forget having to go down to the bottom of the spin tunnel with a broom and sweep the crabs out. It smelled really bad down there. Some of them are still kicking, some of them weren't. All right. So the point in bringing all that up, and then it's kind of fun to see, is one of the things we wanted to do was get the new tunnel out of that flood zone and bring it over on this side into the west area, but also get it out of the major flood zone. Okay. That's all. Does everybody know what tank 1 and tank 2 are, the tow tanks? Yeah, okay. So this chart is just kind of a reminder of the type of work that's going on in the current facilities, the spin tunnel and the 12-foot tunnel. Won't go through all that again, but suffice it to say that we cover a very broad range of the type of work we do. We do ARMD, Aero Research Mission Directorate work. There's the X-59 or low boom flight demonstrator in the upper left-hand corner. A lot of work on what's called urban air mobility or advanced air mobility, where electric vertical takeoff and landing work is going on. We're doing a lot of powered testing, which we didn't do for a long time in those facilities. We're doing it now. But on the space side of the house, we've always, especially in the spin tunnel, have supported the space program all the way back prior to Project Mercury, doing things like landers and things like that, entry vehicles primarily, looking at dynamic stability. We did Mercury, Gemini, Apollo. We've now done Orion. We've done commercial crew, both Blue Origin and SpaceX, and we're doing a lot of planetary probes like Venus probes. You see there in the bottom, second from the left, and we're doing the Firefly mission, or excuse me, the Dragonfly mission that's going to go to Titan, moon of Saturn. So a whole lot of really interesting work going on, extremely versatile, and that we're going to continue that type of work in these facilities. So this is a schematic of the Flight Dynamics Research Facility. So it's what's called a double return. And for those of you who've been around a while, you remember full scale tunnel, of course, and it was a double return tunnel. There aren't that many of those, but there's, form follows function. So when we did the trade-offs with the designers to look at, what's the best shape for this facility, we looked at both single return and double return tunnels, or they did, and we were in part of that process. And for a lot of reasons, the double return won out. It has drawbacks. It has advantages. Advantages are you get to build a shorter building. As it is, the FDRF, if you've driven by it, it's 136 or 132?
132. Yeah.
132 feet tall, which when one of the, the gantry is taller, but once that's not there one of these days, this is going to be the tallest building on the field. So we have the Air Force Base next door, those things like that to think about. The single return tunnel was another, I forget how many more.
215.
215. So that very tall, slender structure that brings in all kinds of problems with structural flexibility and building structure. And so we settle on the double return. You can see the test section here in the middle. That's in this level. It doesn't show up. The control room is at that level. It's about 6 stories up if you're counting. And if you're counting steps, it's 125. 125. Yes, it is. And so it's powered by 4 fans that are down at the bottom. And I know someone's going to want to know why the fans are down at the bottom. I'll talk about that in a minute. But we have four fans down there. We'll give you some more of the details in a minute. Pushing air through heat exchangers. This is an actively cooled facility. We have requirements that the air temperature does not exceed 79 degrees at our maximum. It's not our maximum velocity, but it's at the maximum test velocity that we're going to be using. And then goes through, of course, the usual turning vanes, honeycombs, and screens and a contraction before going up and being circulated back around. They're 750 horsepower each, so we have 4 of those.
14-foot diameter.
Yeah, 14-foot diameter carbon fiber fans, 8-bladed fans. And we'll show you a picture of it in a minute. And when you all come through, and hopefully all of you can come in April, you'll get to see that, I hope. This is just a quick schematic of the ground floor. There's basically 2 levels of this thing. This is the ground floor. And so the entry point is right here at the front, the lobby. We have a really cool lobby concept for those interested. Because we have so much history and so many artifacts from the existing facilities, we put a lot of thought into what the lobby is going to look like. All that's there is an entry and an elevator, basically. But we have, you notice this wall here is curved. So we've come up with a timeline, a pictorial timeline, starting at the beginning with, when 12-foot came online, and it moves from right to left around that curved wall through the decades. And we'll have examples of, people and models under test in the facilities. Our digital graphics guy, Lee Pollard, is working with me on that, and some others as well, to come up with the right photos. But it's going to curve around until it ends up at a big touch screen monitor that's going to have like what's going on today, but it'll go through all those decades until, it ends with tunnel comes online. Here's what's going on right now. Here's what's going to go on in the future, and that'll be changeable. We also have a beautiful display case, floor to ceiling display case. It's, how long is it? 18 feet?
I think so, yeah.
18 feet long, floor to ceiling. That's going to have a lot of the models and other test articles and artifacts going back to the 30s. So that's really neat. So you have an elevator here that brings us up to the control room level. Everything back here is kind of back of the house, storage systems and whatnot. The fan motors I just talked about are here in the center, 1, 2, 3, 4, with the turning vanes right in the middle. And then the very back of the house are all the pumps for the cooling system. On either side, we have VFDs, or variable frequency drives, which is how the motors are powered and controlled. Those are in these rooms back here. So these are not areas that will be accessed by the public, only really the lobby. So going up to the control room level, this is just a kind of an overview of it. It's deceptive. Well, it's a lot bigger when you see it in person. Let me just put it that way. To calibrate you, this is 20 feet across for the test section diameter, which is the same as the current spin tunnel. We have our control consoles for the operators here. What you see here on the right, and everything in red, by the way, are items that are coming over from the existing facilities. Part of our, I started to say this earlier, but I didn't finish my sentence, I think. part of the way we were able to make the case for this is we have a lot of, even though the tunnels themselves are very old and in need of a lot of maintenance, the test rigs, the data systems, and all that kind of instrumentation has been kept up to date. So we don't need to reinvent all that stuff. We're going to bring that over with us. So that's phase 2 of this project, which we're getting pretty close to getting to. And Dave will talk about that a bit. But on the right here, we have what's called the rotary balance system, which is out of the vertical spin tunnel. This allows us to do various types of very unique dynamic motions for doing all kinds of different kinds of tests. What's here at this 6 o'clock position is what's called the C strut, which is our test rig out of the 12-foot tunnel. That allows different types of dynamic motions to be made, and it also can handle much heavier test articles than the rotary balance. So we have, between the two, we have a real spectrum of capability that we're bringing in. The beauty also of the way we're doing this, unlike in the current facilities where the test rigs are either fixed in place or at best can push up against the side of the test section and kind of nest up against the wall, but they still hang out in the breeze. These are fully injectable and retractable. So we can be doing testing on one of the rigs while we're building up a model on the other rig, or we can have both of them pulled out, and we can be doing a third type of testing through a hatch up at this, about the 2 o'clock position, for free flight testing, where we, just like in the spin tunnel now, we can launch a dynamically scaled free flying model. It could be a capsule, it could be an aircraft, and look for spin modes or dynamic stability or whatever, what have you. We also have laser and smoke systems for flow visualization. We have the ability to do surface pressures and kind of the usual things. So over on the right side of the floor plan here is kind of what we call, Dave and I have started calling the industrial side of the building. That's where the technicians are going to be, their workbenches, the model build-up areas, the data system patch panels, and all that kind of thing. On the left is going to be where where the operators are. We're going to have large workspace tables here with monitors to project data. If you want to be a little bit away from the test section and want to be looking at data or having a phone call or whatever. And then over here at this bottom left is a break room. Right now it's fully open, but it has a little kitchenette, and we're hoping to have it glassed off if we have enough money at the end to give a little bit of seclusion, like for a quieter conversation, but it'll place for the crew or the staff to take a little bit of a break. I will point out also that we have restrooms, and that was not in the original plan, because we're sited, I'm sure you've seen it by now, we're sited over here by the old Building 1200 location, which has been now torn down. The original site was actually on the 7x10 footprint, which had been already torn down when we started this, next to Building 1212. Well, the branch that operates the current facilities already has a lab in that building. And so the idea is, well, we'll just build this right next to it on the old 7x10 site. We've already got the lab, we got a little office space, and we have a restroom. So we don't need a restroom in the tunnel. And I made that a comment in a meeting one time in one of our early design meetings, and a technician almost came across the table and grabbed me around the neck. He said, I need to have access to a restroom very quickly sometimes. We are not leaving the building to go to the bathroom. So we did even better. We got 2 of them. So we're good.
So we may actually still end up with the same grabber. I think we'll avoid having the box that cantilevers 20 feet out the side of the building to stow it. As part of the requirements for the overall project, the contractor owes us essentially like the technical solutions for how we operate and maintain the facility. So we'll say that they're having a little difficulty right now seeing much further than a week or 2 in advance, and I don't think they've given a whole lot of thought to what that solution is yet. So I'm not sure that they're going to come to us with anything more inspiring than the grabber. But as Mike has mentioned, like the grabber has worked for decades now, so I assume we're going to have something similar to that.
So if you don't know what the grabber is, when we do free flight testing in the spin tunnel, there's a net down at the bottom, and there'll be a net in this one as well. And so when you fly a model and the test is over, you turn the tunnel off, the model falls down into the net and has to be retrieved. So we have a very long pole that has a claw in the end, and a technician can actually reach down and grab it with the claw and pull it back up. And many years ago, somebody figured out that thing is pretty heavy. So let's go grab a parachute from the hangar, probably off of an ejection seat or something, a little drogue chute. And there's a parachute on the end of it that helps lift up the model as you come back. It's actually pretty ingenious. So we need something like that in the new facility, but there've been all kind of exotic proposals like flying a UAS down there and grabbing it. But we'll probably end up with the grabber.
Yeah.
It's my guess too. I'd just like to show this, and I haven't been good about using my laser pointer online. Sorry, folks. As I pointed out, this test section diameter is 20 feet. And by the way, it's 12-sided. It's not really a circle, but we still call it diameter. That's both the FDRF and the spindle have that same diameter. This outer circle is the inner wall of the control room of the spindle. I just like to point out the difference in land area we're going to have for folks to work in. It's pretty dramatic. And but like anytime you move into a bigger house, you think you have all the room in the world until you fill the whole thing up, and you need a bigger one. So I fully expect that to happen.
That was actually kind of just a happy coincidence with the design too, because we didn't have a set requirement for how much space we needed. We did have a long list of like, all this stuff has to come over from the existing tunnels, and we need to be able to perform certain activities. But really, once they, if you go back to that original aero line drawing, once they figured out that and the building structure necessary to support and access that, it really just kind of made sense. There's kind of 5 central shafts of the building. You got the 2 return air towers, 2 stair towers, and then a center shaft, kind of bottom center of the photo, which has the elevator and utility chase, and just made kind of economic sense structurally to just span all the way across those, and that became essentially the entire second floor of the facility.
So just to point out, and we've sort of talked about a little of this already, but some of the test techniques, we were just talking about free spin and having to use the grabber to get a model. So this is an example. This happens to be an F-18E model 30 years ago being tested with actually a spin chute on the back, if you can see it up here. And when that test is over, it falls to the bottom. It has to be retrieved. And just as a kind of point of reference, a test like that, I think for that test, I counted up something in excess of 800 separate launches of the model into the tunnel and retrievals, because you have to test such a large matrix of test conditions, and it's kind of it's a nonlinear problem, so it's hard to extrapolate and say, well, if it's good here, it's good there. So a lot of that goes on in that type of testing. This is what's called steady coning. That's the rotary balance. So a model it's a captive test, just like in a typical wind tunnel, except now it can rotate about the velocity vector. So you're sort of simulating a spinning motion like an aircraft spin, and you can measure with an internal balance, 6-component balance. You can measure the forces and moments. You can take that data, you can do analysis on it to predict spin modes, or you can put it in a simulation database and use that as part of your 6 degree of freedom simulation, just like static data is used in addition to the static data. That rig also has what's called a forced oscillation motor on it. So we can have the rig stationary and do the typical sinusoidal forced oscillation that some of you are quite familiar with, to get the dynamic derivatives, the damping coefficients, if you will. But in this case, because it's on the rotary balance, we can rotate it and oscillate it at the same time, which gives you some really dizzying type motion. And it's kind of a unique case where you need that kind of motion. But we've had cases, and I'll give you an example. During the Orion buildup with the Orion under the parachutes, they were doing drop tests out at the Yuma Proving Ground on full-scale boilerplate capsules. And the motions they were seeing of the drop out of a C-17 were not matching up with the simulations that they were using at the time. And so a man in my old branch, Dr. Bruce Owens, thought we should do some testing on the combined motion rig, doing rotary and oscillation, because he just, looking at the videos, he could tell it was kind of a combined motion. And so they did that type of testing, got some data, and implemented that in the models, and got a lot closer matches to the flight data. So it just kind of makes the point that sometimes you need to look under a different rock. The final thing is, yes, sir.
Are you talking to me, Mike?
Yes, Mike. Okay.
Sorry, I didn't catch that part. Since you're doing propulsive testing with rotating bladed systems, they're notorious for not always staying where they're designed to stay. Did you have to do any kind of special debris containment, or are there any limitations or restrictions on sizes and weights of the rotating models you have and things like that?
Yes and yes. That was one of the first things that came up when we were starting the design was because we knew this kind of power testing was going to probably get bigger, and it has. We did some analysis internally and turned that over to the contractor on what kind of ballistic impacts we could have with a lost blade. And we made some assumptions about blade size. I think it was a 15-inch diameter blade, if I'm not mistaken. Assumed a material. I forget if it was wood or whatever it was, but we had to make some kind of assumptions, but we did all that and turned that over. And so when in the design, between the Lexan, it's double pane. We have double pane on all the transparencies. It's Lexan on the inside and glass on the outside, if I remember right. And we have sandwich type metal skin on the test section. So the answer is yes. And because that was a real concern of a lost blade coming through a window and things like that. Mike, does that help? And Dave's got another point.
Yeah, we had acoustic requirements as well for what the noise level in the control room could be. The idea, the interest is that when testing with the test section completely closed up, so not in free flight mode, that you wouldn't have to wear hearing protection, when working in the tunnel. And so the test section walls, I want to say they're 5 inches thick. It might be 4, but I think it's 12 gauge skins on either side. There's some acoustic batting in there, but there's a half-inch layer of Kevlar reinforced panel, which essentially is the same product that I've built into like judges' benches in courtrooms before. So it's capable of stopping a handful of 357 slugs, fired at the same spot over and over. So that's there to basically take the initial abuse of a blade that gets loose as it comes through, the sandwich panel.
Thank you.
Yeah. We had one more question online from Robert Stoiber.
Hey, Bob.
Hey, Mike. Good presentation. Good to see you. A number of years ago, I remember dynamic pitch and plunge was one of the up and coming test techniques. Do you have a need to do that in this tunnel?
Yeah, that was one of those that seemed to kind of maybe fizzle out a little bit. Of course, the Virginia Tech still has that capability that they built into the old stability tunnel that Langley gave them. But to my knowledge, it hasn't been used a whole lot. It may have been used in some academic type exercises and research, Bob, but we have not really had any request or motivation, if that's the right word, to use that technique. So yeah, that's about all I can say about that.
Okay, thank you.
Sure. Okay, let's see. Where else was I going to go? Oh, and before I leave the chart, back to Mike Marcolini and anybody else who's kind of acoustically oriented. One of the requirements that we had on the facility, because we're built right next door to the acoustics folks, right? Building 1208. And there was some concern, and understandable, about, well, how noisy is this thing going to be? Are we going to be able to do our human subjects in the quiet rooms when this is rolling and all that? So we, a group of us went down to actually the iFly tunnel in Virginia Beach several years ago with a bunch of acoustics meters, and they were very, very accommodating. They brought us all through. We took readings inside, took them outside, up at high speeds, at low speeds, and all that. And so the acoustics folks said, okay, at the boundary, at the fence line between our two buildings, here's the maximum sound pressure we can tolerate and still do our stuff. I don't know what magic they did to come up with those numbers, but they did it. And so that actually went into the requirements as well, not just interior noise, but exterior noise. Dave always likes to point out that F-22s make a lot more noise than we're going to make, but be that may. But to that point, things like in the design, we have a 500-ton air conditioning chiller sitting out there to cool the tunnel, to keep it under temperature. It's a huge, huge unit. And we put it behind, the designers put it behind a sound wall on the opposite side from building 1208 to try to, again, mitigate that noise concern. Okay, rolling on. The previous chart was all spin tunnel kind of test techniques and rigs that are coming over. This is out of the 12-foot tunnel. I think I did point out that this is the C strut, which is just the typical rig has a 0 to 90 plus angle of attack or pitch range. that we use. It also has a side slip capability. We have smoke flow, laser light sheet smoke flow to visualize things like vortices. This is both on the X-59 when it was in the tunnel. We have the roll, pitch, and yaw capability for doing forced oscillation. And then we have a relatively new, not new concept, but a new test rig in the 12-foot tunnel called 3 Degree of Freedom, where we're doing powered testing on a 3 Degree of Freedom rig, so all rotational degrees of freedom. And we have an active closed loop control system running. So we're doing, at the same time, we're doing design of experiments type testing with system identification running. And these guys have been able to reduce the test time relative to doing a straight one factor at a time test campaign by a factor of an order of magnitude, basically. So it's really, really, really encouraging, and it's applicable beyond just doing the power testing. But this is where they've used it so far, and they've done. I think we had 4 AIAA papers at SciTech on it this year, and we had a paper on FDRF there as well. Okay, I think the next one's my last chart, and then I'm gonna turn it over to Dave. Okay, so just again, because y'all are going to come into the building hopefully in a month or so. These are some artist concepts for what the interior will look like. Some of them are a little bit dated, but on the left, you see upper left, you see the control room with the consoles I've already pointed out from the overhead view. And just kind of mentally kind of put in your mind that all these pictures have these bright, shiny floors. Guarantee you they are not going to be bright and shiny very long when they start dragging stuff across the floor upstairs.
A lot of house plants.
Yeah. Yeah, a lot of house plants, a lot of ferns. The middle picture and the right are the other views of the control room, both the industrial area in the center and then the more research area on the right. The lobby I already described, although that's a very dated picture because the display case is much larger than that, and I don't think we're going to have any yellow on the wall either.
Nope. Yeah.
And then, of course, the little kitchen area that's kind of bare looking right there, but it's actually a little nicer than that. Okay, so Dave, I think this is where you take it. The clicker's on the right.
So as Mike mentioned, it's a design build contract. So a lot of the requirements for the performance of the facility really just center around what the conditions we needed in the test section are. We're executing this in partnership with GSA, which comes with its own challenges, right? When you're kind of working with another agency. But part of that is because we're able to leverage their kind of larger contracting apparatus and the experience they have. I mean, they build a lot more buildings than we do, right? And so this one's a unique building, but it's given us the opportunity to really kind of focus on the kind of uniquely NASA aspects of the facility and not have to be as worried about like fire alarm system and like routine building systems that GSA has more experience getting together. And we went through a 2-phase solicitation process. So they sent out, and this actually predates my time on the project and with NASA. We sent out an RFQ, request for qualification, got back 6 interested parties, I think. And at the end of that process, this was like 2019, 2020 timeframe, down selected to 3 teams that we felt were the most competitive to deliver this facility. Went through then another year and change of that kind of phase 2 process, which was the RFP. That culminated with those 3 offerers submitting a technical proposal, which included a concept design for the facility, which you might say is 30%. I think we'd probably argue maybe they were like 10%, like type level of concept. But essentially enough of a design to show us like what it would be and some rudimentary work that would demonstrate that the facility can meet the flow requirements that we have for the test section and the other set of performance criteria. We gave them 2 options to prove that out, kind of initially, and then talk about what their plan was to prove it out in design. One was with some CFD modeling, and the other was with actual like empirical data from an analog facility. And went through that process. I'll say that all of the bids came back so high initially that the contracting officer refused to even disclose to us what the amounts were. So it was so far out of our budget that she felt that she couldn't even in good faith enter into negotiations with the offers. So she came back to us and said, you either need to ask for less building or bring me more money. CFF project, so we set to work trying to figure out how to get less building. So we took pretty heavy-handed approach to some of the requirements. The top speed of the facility that we were asking for went from 47 PSF, dynamic pressure, down to 20, with an option to buy back in if we can afford it to get to 35. We axed the active cooling of the facility, and we're going to have a passive cooling system, probably with back pressure screens and louvers, with an additive option to get active cooling back in. I think we changed some of the acceleration deceleration requirements for the fans in there. And at the end of that process, we had a team that had a number that was within range to start to negotiate on, and that's who got this project. That team is a combination of Beal Harbert International, which is a large firm out of Birmingham, Alabama, and they've partnered with kind of two different design firms, kind of a classical architectural engineering firm called Mason Hanger, that has big office up in the Richmond area, some offices up in DC. They do a lot of government work. They've done embassies and stuff like that. They've worked with Beal Harbert on projects overseas as well. One of Harbert's mottos is build anything anywhere. And they've got a very extensive logistics operation where they've done a couple of embassy projects where every single component of that facility overseas passes through their logistics warehouse in Alabama, gets inspected, inventoried, and then palletized at a point to be delivered to the job site at the point in which they need it for construction. So they seem to have, while they've never built a wind tunnel before, a lot of experience in managing some very technically complex and logistically complex projects. We got Mason Hanger, and then they also partnered with what was Calspan ASE Fluidine out of St. Paul, Minnesota, has since been spun off as a new company called Northwind. They are the wind tunnel designer of record and also a subcontractor to Beal Harbert, doing some kind of essentially like a mini design build contract. They're furnishing a lot of the hardware kind of specific to the wind tunnel. At one point in the solicitation process, they approached us with an RFI and said, GSA has a prohibition on using precast concrete on the project. Would you be open to entertaining a deviation to that requirement? We kind of huddled, got into the root of why GSA had that prohibition. I don't know if anyone's a concrete person, but you can pre-stress concrete or you can post-stress concrete. And GSA's prohibition was kind of just blanket apply, but really their concern was post-stressing concrete. It's a process where you kind of form cast and then you pull tendons under significant amount of tension, clamp them off, and you use the tensile strength of that product, usually steel, to kind of keep the concrete in compression all the time, so that you can then essentially use concrete members in a capacity where they typically otherwise wouldn't perform well, right? Where that member would be in tension, like on the bottom side of a beam. And so we agreed that pre-stressed concrete would be acceptable. So they came back. That's ultimately how they got their number in the box. They later shared with me that by us allowing them to use pre-stressed concrete on this project, pre-stressed precast concrete, they saved $1 million simply in the savings it would take to install a soffited ceiling area underneath the control room outside, right, to stop birds from roosting in there. So significant savings in that regard, just in terms of what it would take to scaffold the outside of a building where the structure was essentially in one piece that goes in. It's everything from the interior surface in a lot of parts of the building to the insulation for the thermal envelope to the outside of the building and the drainage plane in there, as far as how you keep the building weather tight. So pretty effective in that regard. Yes. Okay. So I'm going to flip through these relatively quickly. We had some aerial photographs taken during construction. We've got a precast driven pile foundation. This is as we're coming out of the ground. You can see there in January of 2023. In March, 2 months later, we're kind of well on our way out of the ground with that precast construction. Those panels were cast up in Tyndall Corporation, which in Petersburg, south of Richmond, and then shipped down here on trucks, erected kind of as they were delivered by a crawler crane on site. And there's 450 panels overall that comprise the building. Then 3 months after that, we basically kind of reached the limit just about of where they could go vertically before they had to start tying in the control room level. And before we did that, we needed them to set the fans in place. So in this kind of bottom right corner, they've been working on assembling various components of the fans, the actual fan section, an inlet section, diffuser section, and then starting to drop those into place. Once the fans were set in, they continued to climb, and we paused one more time to set the contraction section in place. That was also completely assembled on the ground. It was mostly assembled at the factory where they fabricated it before they shipped it down here. But then that was assembled on the ground, lifted and picked, a single lift with the crane. It's about a 90,000 pound load that they set in place, kind of fished it down between the columns there to set there on top of the stilling chamber area. And then once that was in place, that set them, loose to basically set in the control room floor, the control room roof, top out the air towers, start hanging the skin. I think in this photo you can see in that on the left-hand side, they're starting to hang kind of the skin. You can see like the bottom parts of some of the window openings there. That are the rest of the facility. We paused one more time. I don't have a good photo of it in this presentation. We've got that big square hole in the roof, right? So they also, while this was shortly before or after this photo was taken, we started to assemble the test sections. That was all also put together off on the right-hand side on that big concrete slab you see. And that was lifted in one big assembly, fished down through the opening in the roof there, and anchored off to where it currently sits. And then that freed them up to basically finish the rest of the facility. So on the left, you've got the architect's rendering from kind of earlier in the process that Mike had shown earlier in the picture or earlier in the presentation. On the right, we've got a photograph from a few months ago, kind of showing we got pretty close to matching what the architect envisioned. Got a couple other photos there, different perspectives. I think some of the fall colors in the background. Then we got a picture at night shortly after we got some of the exterior lighting systems commissioned. So the NASA logo lights up there, and we've got a number of lights around the outside. You'll be able to get to the contraction section if you were running a second or third shift for testing, as well as trying to highlight that architectural feature of the building. So these are some photos of the inside. So the top row is kind of out of the architectural drawings, their renderings, the concept, and then down on the bottom row, try to match generally that same kind of perspective with photos from, in this case, I guess so. This is back in January of the test section. The floors are done. No, they're not quite as shiny as the renderings. In both these photos, we've got them covered up with some like protective cardboard, board to stop the crews that are still out there working from tearing them up. This is a picture of we got 4 fans. This is a picture of the pair of fans on the east side of the tower, or the east side of the facility. So you get a sense of scale there. So not as big as 14 by 22 or like what full scale had, but still quite large. And then these are some of the renderings for the renderings concepts for how the two test rigs from the existing tunnels will come over. As Mike mentioned, the top left photo, vertical spin tunnel, the rotary balance kind of stows up against the side of the test section, generally gets out of the way, but never fully leaves the airflow. At FDRF, we've got a truss structure anchored to the control room roof and a carriage and rail system that translates the rig in and out of the test section completely. The C-strut in the top right there shown in 12 foot test section. Bottom right, that is also going to be mounted to essentially a linear actuator rail system anchored to the floor in the control room, fully injectable, retractable from the test section. Obviously, also have to kind of adapt that rig. It's currently in a 12-foot tunnel, has a horizontal oriented test section. It'll be adapted to work vertically at FDRF. And then project timeline. So the number one question I get is when's it going to be done? And the number 2 question I get lately is when's ribbon cutting? So as Mike mentioned, we're pretty close to getting to phase 2 of the project. We intentionally structured 2 phases of the contract to minimize the downtime to the ongoing research efforts over at those two tunnels. Like the last thing we wanted is like, we award this project and then day one, they go over and take them offline and then we're down for 3 years. So we're requiring them to essentially demonstrate that they've met the flow criteria we have, those requirements in the empty test section of the tunnel before we let them take those two facilities offline. An hour from now, I'll be upstairs essentially defending the project's readiness to start the integrated testing of the tunnel. So the drive system is complete. The cooling system is operational. We're not quite done checking out the control system in kind of its synthetic environment. The flow path is built, but we're hoping to basically go wind on in the tunnel for the first time about the end of this week. And then we've got about 5 weeks or so of, shaking down the facility, kind of making sure that it can hold and hit its various set points and, fans aren't vibrating excessively and all the other kind of checks that go into making sure the machine is running properly. At about the end of this month, the plan is to go over to vertical spin and 12-foot, have the technicians over there essentially demonstrate that all this stuff works when you came and took it from us, contractor, and then they'll set to, removing it. And some of that's going to come just straight over to FDRF. Some of that's going to take a detour out to a fabrication shop in town to get some, different parts put on it to adapt it to the different geometry at FDRF, and then integrated. And then depending on who you ask, end of May, end of June, I guess the smart money says probably sometime in July, we should be substantially complete with the project. The contractor has another 60-ish days or so to close out. So we'll probably still be wrapping up things on the project into September. But the goal is that the research branch that operates this facility should take possession of it sometime by the end of July and be able to start their 90-ish day process of characterizing the tunnel before they start doing, kind of new research in it. And I'll probably ask Mike to join me up here if there's any more questions. I know we've run over a little bit as well. I don't know the wind speed off the top of my head, but we had in one of the benefits of using GSA and just kind of classical construction approach, like the building code requires certain wind speeds given our, zone, where we live relative to the Atlantic Ocean and hurricanes. So I forget the exact wind speed, but that was factored into the requirements for what it needs to be able to endure. Yep.
And I'll make the other point that the two openings were not a requirement on our part, but I think, that they didn't do it because of the wind speed, but that actually has worked in their favor to reduce the wind loads, because some of the other offers didn't do that.
Yeah.
They thought we wanted everything like storage space, and which would have been nice, but yeah.
Thank you very much.
Thank you.
And we're going to get a picture of you too. We're going to get a picture of you too. Thank you. Great. Yay!